Welcome to section 6.1, Continuous Probability Distributions. In this section, we begin to explore how probability works when dealing with measurements, not just counts. That means we're moving from discrete variables, like the number of texts you send in a day, to continuous variables, like how long you wait in line, how tall someone is, or how far you drive. These models are especially useful when we want to describe the likelihood of a range of outcomes, such as the chance that you'll spend between 8 and 10 minutes commuting to class. We'll explore the mathematics and intuition behind uniform and exponential distributions, both of which are foundational in business, engineering, and science. A continuous random variable is one that can take any value within a given interval. This is different from discrete variables where the values are countable. Think about something like body temperature. It could be 98.2 degrees Fahrenheit, 98.24 degrees Fahrenheit, or 98.243 degrees Fahrenheit. In fact, there are infinitely many possible values. Because of this, the probability of getting an exact value, like exactly 98.243 degrees Fahrenheit, is essentially zero. Instead, we care about intervals. What's the chance someone's temperature is between 98.2 degrees Fahrenheit and 98.6 degrees Fahrenheit? This is why we say the probability of x equaling a specific value, a, is equal to 0. For continuous variables, it's not that the value can't occur. It's just that the likelihood of hitting any one specific value on a continuum is infinitesimally small. In the world of continuous probability, we don't use bar graphs or discrete charts. We use smooth curves to represent how likely different values are. The most important thing to remember is area is equal to probability. That is, the probability that a value falls between A and B is equal to the area under the curve from A to B. Just like with a histogram, the total area under the curve must equal 1 because it represents the entire probability space, all possible outcomes. A probability density function, or PDF, is a mathematical function that defines the shape of the distribution. It must always be non-negative, and the total area under the curve must equal 1. For continuous variables, you calculate probabilities using integrals, but don't worry, we'll mostly use Excel or tables to estimate areas. Think of the PDF as a way to tell us where values are more or less likely to fall. Taller parts of the curve indicate values that occur more frequently. Let's start with the simplest continuous distribution, the uniform distribution. Here, all values in the interval are equally likely. If your professor says they'll show up anytime between 10 a.m. and 10:20 a.m., and each minute is equally likely, you're looking at a uniform distribution. The formula for the PDF is 1 over the interval length, b minus a. The mean is simply the midpoint of the interval, so average the endpoints. And the variance measures how spread out the values are. Imagine students arrive randomly between 9 a.m. and 9:20 a.m., a 20-minute window. We want to know the chance a student arrives in the first 5 minutes. So here A is 0 and B is 20. We're interested in the probability of arrival between 0 and 5, arriving in the first 5 minutes. So to get the probability, we're taking the 5-minute interval, that's 5 minus 0, and dividing by the whole 20-minute interval, that's 20 minus 0. That's a 25% chance the student shows up in the first quarter of the time window, right? If this is my whole time window, there are 4 quarters, so a 25% chance they show up in the first window. Uniform distributions are great for modeling schedules, windows of times, and delays. Now let's explore the exponential distribution. This is used when you want to model time between events. This distribution is common in business and science. For example, it could answer questions like, how long until the next customer arrives? Or how long until a computer component fails? Or how long until Thor crashes into something again? The exponential distribution has a unique memoryless property. The probability of an event occurring in the next interval is independent of past events. So our formula is lambda times e to the negative lambda x, where lambda is the rate. And this is only true for positive values. If it's negative, then it's 0. The mean and standard deviation are both 1 over lambda. The graph of an exponential distribution is shown here in this figure. To find areas under this curve, you can use the fact that our probability is equal to E minus lambda A when A is positive to calculate right-tailed probabilities. Left-tailed probabilities can be calculated using the complement rule. Let's say the average wait time at a grocery checkout is 5 minutes. That gives us lambda equals 1 over that 5 minutes, or 0.2. What's the probability you wait more than 10 minutes? So the probability of waiting more than 10 minutes is e to the negative lambda, so 0.2, times 10, or e to the negative 2. If you plug that into a calculator or Excel, you'll get 0.1353. So there's about a 13.5% chance you'll be stuck in line that long. Exponential models like this help with staffing, logistics, and operations planning. And they're used in everything from call centers to server uptimes. Here are the key points from this section. Continuous variables model measurements like time, weight, or length. They differ from discrete variables in that they take on infinite values over intervals. We use probability density functions to model them, and the area under the curve gives us probabilities. The uniform distribution assumes all values are equally likely. It's great for modeling equally spaced probabilities like windows of time. The exponential distribution is used when we want to measure the time until an event occurs, such as customer arrivals, breakdowns, or even respawn times in a video game. These tools are widely used in real-world decision-making. From supply chain logistics to predicting traffic to forecasting failures in tech systems.